In this class, we'll study about the Z transform. For a discrete signal x of n, Z transform pair is capital X of Z. Okay, for a discrete signal x of n, the Z transform pair, the frequency domain, that is X of Z. That means Z transform of signal x of n is X of Z, then the inverse Z transform of the signal x of Z is X of n. Then how to calculate X of Z? Once if you have X of n, summation n minus infinite to plus infinite, X of n Z power minus n. Or otherwise we can also write like Z transform of the discrete signal X of n. Okay, then this is the general Z transform formula. Then the reverse formula is inverse Z transform. Okay, reverse formula is inverse Z transform. That is from X of Z, how to calculate X of n. So X of n is equal to 1 by 2 pi j close to contour integral C X of Z power n minus 1 dz. Okay, in general, we'll be using the first formula, the Z transform formula. But even to calculate the inverse Z transform, mostly we will not be using this formula. This kind of formula you may be studying in complex variables in mathematics, okay, with help of Cauchy residus theorem and all. But here in signal system, we will not be using the inverse Z transform formula mostly, but directly we'll applying the transformation techniques, because first we'll learn the Z transform of the basic signal. From that, directly with the partial fraction technique, directly we'll try to calculate X of n from X of Z. Okay, again the Z transform for a discrete signal. First we have calculated the discrete time Fourier transform. Okay, for a discrete signal we have studied about the discrete time Fourier transform. Now for the same signal we can also write the Z transform. We can also write Z transform. Then what is the difference here? Okay, for a discrete signal, okay, if the signal is discrete, we have, for that signal we have written discrete time Fourier transform. For the same discrete signal we are writing Z transform. You see here, in case of discrete time Fourier transform, the signal has to be absolutely summable. Okay, the main condition here is signal must be absolutely summable, must be absolute summable. Otherwise we cannot write the discrete time Fourier transform, because the summation series has to converge, otherwise we cannot write the discrete time Fourier transform. Whereas in case of Z transform, it could be anything. Okay, the signal need not to be absolutely summable, but here we'll be introducing one extra factor here. Okay, even if the ordinary summation is not converging, that factor will try to converge the series. It will try to converge the divergence series. For that, here we'll be using the ROC concept. Under some condition, under some value of Z, the series will converge. Okay, so that means what? Even if the signal is not absolutely summable, we can write Z transform. That means we can write discrete time Fourier transform for some signals. Okay, whereas we can write Z transform for many signals. That means the signal may be absolutely summable and may not. That means if you are able to find out discrete time Fourier transform, definitely you can find out the Z transform for that signal under some condition, under certain condition, that is ROC. Okay, but if the signal is not absolutely summable, okay, if the signal is not absolutely summable, you can write Z transform, but you cannot write discrete time Fourier transform. That's why I am putting discrete time Fourier transform inside, Z transform outside. So in future, okay, see, for some kind of signal, you can write both Z transform as well as discrete time Fourier transform. That means if the signal is given, you have Z transform, then from the Z transform, if you apply some condition, you will be getting discrete time Fourier transform. Okay, that condition is simply Z equal to e power j omega. So for a signal x of n, you are writing Z transform. Again, definitely the answer consists of Z. Okay, for that Z, if you apply Z equal to e power j omega, then you'll be getting answer. That answer is same as the discrete time Fourier transform of the original signal, that is x of n. Okay, again, in general, here to get the discrete time Fourier transform from Z transform, we are applying Z equal to e power j omega, but in general, Z is equal to r e power j omega. That means for this conversion alone, we are using Z equal to e power j omega. Okay, but in general, Z is equal to r e power j omega. That means during this conversion, we are applying r value as 1. Okay, so now we'll study in detail about what is this Z equal to r e power j omega, what it is implying. Okay, so now we have seen in general Z equal to r e power j omega. Z is a complex variable. Z is a complex variable. Okay, so if it is complex, again, we can also write like x plus jy, okay, in Cartesian format, but this is in polar format. Okay, so whenever it is in polar format, this r is indicating the magnitude, the radius of the circle, generally magnitude. This is giving the phase value, the angle. So we know that a complex number can be denoted with the help of x plus jy format, or otherwise with the help of polar format. So now this r is denoting the radius. Okay, say for example, r is equal to 1. Again, you can be anywhere on this circle. Again, to specify exactly where you are, that will be denoted by this phase, where you are exactly on that circle. Say maybe if you are here, you are with the 45-degree angle. Okay, then that will be denoted here. So that is the concept of polar form. Again, you can go anywhere on the circle. Suppose if you are going here, again your angle is 135 degree. That means that will be denoted here. That's why this omega is variable. Okay, e power j omega. Omega could be anything. So depending on the value of omega, again you may be anywhere on this circle. But say for example here we have taken r is equal to 1. That means at some radius, 1 circle, you can go anywhere on that circle. Suppose if your radius is little bit lesser, say for example if radius is 0.5, then your circle dimension will be lesser than r is equal to 1. Again, you can go anywhere on that circle. That is the concept of polar format. Again, the same thing we can also represent with the help of x plus jy. Okay, you can go anywhere on that circle. Okay, say for example, if you are here, okay, you can denote what is that x value there, what is the y value there, that you can denote with x plus jy. Okay, so with some number here. Again, already you know that the conversion between the x plus jy format and the polar format, that is r e power j omega. Okay, the conversion is in general r is equal to x square plus y square square root. Okay, then what is the angle? The angle is tan inverse. Okay, angle is tan inverse of y by x. Okay, the omega is equal to tan inverse of y by x. Okay, so now the z is a complex number, but that is denoted in terms of polar format. So once if it is polar format, then it is becoming like a circle. Then we know that the similar